So good morning, everybody, and welcome to the Subsea Robotics Technical Webinar for ORCA Hub. My name is Lindsay Wilson. I'm the Hub Manager at ORCA, and today we've got three great speakers from the Subsea Robotics group at Heriot-Watt University. I encourage you to ask them some questions. We've got the chat option, and we've also got a Q&A box at the bottom.
My name is Tomasz Luczynski.
Yeah.
I'm a research fellow at Heriot-Watt, working in ORCA Work Package 1. And today I would like to present some of our results for machine vision solutions for underwater inspection and navigation. And that's all in the context of ORCA Hub. In case you're not very familiar with this, just a very quick reminder of what we do there. So we have four work packages. First one is mapping, surveying, and inspection. Second one, planning, control, and manipulation. Third, work package 3, intelligent human-robot interaction. And finally, work package 4, robot and asset self-certification. So all of our presentations today will be related to work package 1, mapping, surveying, and inspection. And ORCA Hub is quite unique in this regard that it tries to bridge the gap between early research and commercialization. So on the TRL scale, we try to move between levels 3 and 6. And keeping this in mind, I will discuss solutions that we've developed following these TRL scales, starting from the bottom and ending with solutions which are ready for commercialization. Again, if we want to have something applied and really used, we have to focus on some key problems. First one being robustness. Demonstrating something that works once is not good enough for us. We want something that works in a wide range of conditions, which is a tool that we can rely on. And we need it to work in real time because underwater vehicles often cannot be connected to the surface with bandwidth required to any kind of computation happening on the surface. Or this connection is not reliable enough to run it this way. So preferably everything should run on the vehicle in real time. And these two factors, so robustness and real-time performance, are key enablers for autonomy. And this is our end goal. We want underwater vehicles to move autonomously, perform the most challenging tasks autonomously, and that's what we're working towards. And within work package 1, we focus on solutions based on SLAM, SLAM being simultaneous localization and mapping, based on supported vision. By supported vision, I mean that it's the main source of information are cameras for moving around and localizing ourselves. But we also fuse this visual information with other sensors like IMU and DBL for best possible performance. And finally, we would not only want to have a 3D map in the end of the mission, but also have some understanding of what's in front of us and what does it mean for the objective of the mission. Hence, we also work on semantic mapping and scene understanding. Okay, so starting with our solutions on the TRL scale, levels 1 to 3, so early research and stuff that is not really well developed yet. First point that I would like to make is semantic mapping, which for some tasks it's higher, but in general I put it on the low TRL levels because these solutions are application specific. So depending on what exactly we want to do, we might need to do extra development. Some of these things are more advanced, but that's still relatively early level and very much ongoing research. And then second point, which we just started to work on, is visual localization in open water, which means that we have a few ideas on how to get some information about how we're moving in open water purely from video without having any objects in the field of view to track. So this could support localization on the way to the structure rather than while moving around the structure. Again, this is still relatively early level, not much to show in terms of results yet. That's why let's jump quickly to TRL 4 to 5, and these are very exciting results. This particular work is by one of our PhD students. So here we compare his SLAM approach to ORB SLAM 3, which is state of the art. And every now and then he introduced black frames, which corresponds to loss of visual features. So either very bad visibility or something occluding the field of view. And you can see that ORB SLAM 3 creates submaps, but in between these maps, it's completely lost. It doesn't know how to join it. In our approach, these submaps are much better aligned to begin with, and after moving a while in the region, for a while, you can actually rejoin these maps together and get to a consistent single map. And the calculated path taken by the vehicle agrees with the ground truth that we had for this experiment. So that's a great success, and this was also tested offshore. So these are data. This is data recorded offshore. As you can see in the video, very challenging conditions. And even though we didn't have ground truth for this, just assessing the quality of the result, visually it looks like it's correct solution. So everything that should be straight pipes look like pipes. And again, this data set was very challenging to the point that we didn't think it would be of any use at all. And yet it managed to, this algorithm manages to work in these conditions. And thanks to that, we are able to develop a more holistic approach to autonomous inspection. I don't want to go into this bit of work because this will be discussed in details in the next presentations. So just a hint that that's very much ongoing research. I put it on TRL 4 to 5. It's being developed very quickly, so possibly it's on the verge of 5 to 6 at the moment. Yeah, and this allows to have inspection executed fully autonomously without any intervention from the pilot side. Okay, and TRL level 6 to 9. From our perspective, this means that these are solutions which are fully developed for our research. This is our toolbox of things that we use and things that we rely on. So camera calibration and image rectification. The problem is that when you take your cameras underwater and you want to perform 3D reconstruction, all the images are distorted because of the refraction on the water glass air interface in the camera housing. And these distortions are very hard to rectify, to correct, because an image doesn't have a single viewpoint anymore. In a way, it's as if every pixel has slightly different focal length. And we have a method which allows not only to correct those, but you don't have to do any procedure on site. So you don't have to calibrate the camera in water, even though these distortions depend on water temperature, salinity, and pressure. So very much conditions that they can change from side to side. We just have to calibrate the cameras once in air and then know these parameters of water to predict the camera parameters. In this experiment that you can see on the video, point clouds were just accumulated according to the vehicle odometry. So if there was any error in the image rectification, you would see each point cloud being slightly warped. And once they're overlaid, you will just see a lot of points flying in air. And as you can see, we have very smooth surface with no extra points on the right locations, which is a good indicator of very precise rectification, which is exactly what we want. So this allows us for getting 3D reconstruction on exactly the same level as algorithms working in air, pretty much ignoring the fact that we are underwater. Yeah, that's just a summary of the map from these experiments. Just a point cloud from that location. And then second solution, which is also on, I estimate, TRL 6 to 9, is image enhancement, where this algorithm merges multiple factors and multiple solutions into one very compact algorithm. So that's why I will show you a few experiments. aiming at different things. So in this video, on the left, you have raw footage where we change the illumination. So we change the light temperature, we change the light intensity, which is very common underwater when you approach the structure. But this can influence how you detect features underwater. So this perceived change in the light and features can result in losing track of these features. So this algorithm tries to minimize these differences. As you will see, if the image is oversaturated, there's not much we can do about it. But otherwise, this perceived change is minimized, which helps with tracking over changing environmental and illumination conditions. So that's just one facet of the algorithm, and this is exactly the same algorithm running on in a different setup. So very dark setup, low light, and we have a board with markers, and we try to recognize these markers, detect them, and the vehicle is moving towards the wall where these markers are. And you can see that in the enhanced video, we already have a very stable recognition of the marker. Whereas in the raw image, exactly the same algorithm is still not capable of finding the marker. Eventually it does, but we got an improvement in this experiment of over 2 meters in terms of distance, where we were able to reliably recognize the marker. And this marker is just an easy way of simulating some kind of visual feature that we can find in the environment. So as you will see later, this allows us to have any vision-based image recognition, object recognition, and localization methods just working more robustly. It extends the range in which we can successfully use whatever approach we decide to go with. And then finally, exactly the same algorithm again, just this time working in open water. On the left, you have raw frame as recorded from the camera. On the right is being enhanced in real time. The slight lag in the video is coming from the communication layer, not from the algorithm. The algorithm works up to 40 Hertz now on the stereo setup, so 2 streams of videos. Yeah, and it's just this one image enhancement algorithm. So we could technically also improve colors. We could saturate it more. I didn't want to do it in this video just to demonstrate this one algorithm rather than combined approach. I will pause here. And you can see that in a way, the algorithm, maybe I will jump to an early stage. Here on the side of the structure, algorithm is in a way it's aware of differences in the enhancement that it needs to make in different parts of the video. So on the left on the image where there's pretty much nothing there, it still attempts to pull all the information that might be there. That's why effectively you get this sensor noise. And in a place where there is structure close by, you don't, so if you try to do the same level of enhancement, everything could be pretty much over enhanced and destroyed. Here you don't have this effect. It's adaptively reacting to what's in the frame. And if there is nothing or very little, it tries to be more aggressive. If there is already information in the image, it's a bit more conservative. So you get the most of the data that you recorded. That being said, it's purely passive approach. So it has to have some residual information in the image in the first place. If the image is just broken, so there's just nothing there, then unfortunately we can't do anything about it. But that's very much the nature of what we wanted to achieve. So here we tested it in the context of mapping. So in the left video, we tried to map. It's one of the structures in our research tank. It's like artificial beach. And you can see that even though it does some kind of mapping, it's very noisy and it should be straight, and it put it in this band shape. And that's because all the features that it could match were very, very hazy. And then after enhancing the image, exactly the same algorithm with exactly the same parameters can reconstruct the structure and navigate on this without any problems, with much higher accuracy and no noise whatsoever, which is exactly what we wanted and which is exactly what we observed. So as long as we have any residual information, we can quite reliably operate around the structure. That being said, sometimes we just come to a location like harbor after the rain, where visibility is 10, 15 centimeters, and unfortunately we cannot do anything about it. But that's quite rare, and this was to be expected in the first place. Okay, so this concludes my presentation, and thank you for your attention, and any questions are welcome.
If you can stop sharing, I shall pass to Jonatan.
Good morning. I'm Jonatan Scharff Willners, and I'm a research associate for ORCA Hub at Heriot-Watt University as well. And I would continue this presentation by talking about how we use autonomy for underwater robotics and how we incorporate all the visual aspects that Tomasz has presented. And to continue on the same motivation, I will instead focus on how we can use autonomy for robust online systems. And the motivation behind the work is that autonomous marine vehicles are seeing an increased usage every year. Conventionally, these operations are performed from support ships. This includes a significant amount of humans to be involved, both as a crew for the ship as well as for operating the ROVs. As the ocean is a very harsh and unforgiving place, this is a very dangerous task. So by using autonomous underwater vehicles, we can remove humans from on-site operations and allowing them to be safe at shore instead. An additional advantage of this is that we can reduce the cost for operations as well as environmental impact, as we no longer need these large support ships during the operations. And AVs has a wide field of usage, and while I will focus on two aspects for mapping, namely inspection and exploration, they are also being used for mapping for environmental observations and applications. In our group, we're also working on maintenance, such as intervention, which can be seen in the picture where our AUV is equipped with a manipulator. Likewise, what can be seen in the image is some marine growth, which regularly should be cleaned to maintain the structure. AVs are also used to cover large areas for search and rescue missions, for example, such as finding people or missing airplanes. It's also seen quite a lot of usage in deep sea operation, as well as in defense sector, for example, mine countermeasurements. During visual inspection of offshore assets, it is easy to lose tracking of the visual features used for simultaneous localization and mapping. There are multiple causes for this. As we've seen previously, it could be environmental, as turbidity and inadequate water conditions, or internal, as in error and noise related to dead reckoning for pose estimation based on the navigational sensors. At sea, we also have lots of external forces, such as waves and current, that can push the vehicle out of its desired position. And when visual tracking is lost, our SLAM system relies completely on dead reckoning and has no external features to update its position towards. Therefore, until our visual features are regained, the error and uncertainty can grow without bound. To counter this, we have developed a framework for robust inspection based on autonomous relocalization. This work improves the success rate as well as the quality and the survivability of the system during its mission. The framework for this we have called Situational Evaluation and Awareness, C, which combines knowledge of mission failure characteristics with planning for current states to provide system robustness over long time periods. Of this while maintaining the quality of the information gathering and the goal execution. And I will not go in much more to this because Yaniel will discuss this in much more detail in his presentation after mine. The framework adapts to new information when new error occurs during the mission. And one of these errors could be the loss of the visual features to track. When this happens, the SLAM system notifies that it's currently lost along with the prior keyframes, And these keyframes are used to generate a temporal plan that has a high probability of performing a loop closure with the prior map. And when the robot has successfully managed to relocalize, the temporal plan is completed and the robot can continue with its main objective. We have integrated this with an ROV, which has been customized to be autonomous by adding what we call an autonomous underwater inspection payload. And this can act as a backseat driver, and it includes the stereo camera system that we have seen in the previous presentation, as well as additional sensors such as DVL, IMU, fiber optic gyro, and depth sensor, so that we can have post estimation at all time, even at the times when we lose visual feature tracking. In the video, you can see how an autonomous inspection of an artificial structure is performed while we're using the framework for autonomous relocalization. To show the efficiency of the approach, we force the vehicle to lose tracking by blacking out the cameras at set states of the mission. And by doing this in repeated inspections, we can compare how our approach has performed compared to not using an active relocalization and just using a traditional waypoint following algorithm. And as seen, the robot manages to relocalize when it's lost and is able to keep a single consistent map throughout the mission. In the video, you can see when a map of a new color is presented, it has lost track and it will try to merge, find a temporal plan that will merge the new map to the old map. The keyframes it's basing its new temporal plan can be seen as the green arrows, and the orange ones are the one it has found that it should visit to increase the probability of actually performing this map merge. So it has now almost finished a complete lap around the structure, and after that it will return to a safe recovered position. And here it can be seen that using the presented framework, the robot managed to keep a single map in the end of a mission, while the compared approaches results in multiple submaps. As seen, the submaps are not properly aligned, which can cause error and lower quality constructions. Likewise, if it has multiple maps, it can result in a worse post-estimation, which can potentially grow with each submap until the robot cannot properly navigate in a global map anymore. In the graph, you can see that how when our approach creates a new map, it can quickly manage to relocalize with the initial map to keep the single map, while the other approaches has an continuously increased amount of number of maps. The autonomous relocalization framework can be applied to many scenarios. We have seen it being used for inspection in the previous video, when the structure is known and a mission can be planned in advance. If the structure is known, we can find a set of viewpoints that can efficiently provide a full sensor coverage of the environment. This can either be generated based on the geometry of the structure or a CAD model. And seen in the bottom right, we have had a CAD model where we have generated a set of viewpoints, and then that completes a full coverage of the structure, as well as finding an optimal path that the robot should take to visit all of the said points. However, much of the ocean is unexplored, and we don't always have access to data about the target or the structure of interest. In such cases, the optimization approaches to find an optimal path for complete sensor coverage cannot be used. Instead, the robot will need to explore the structure and continuously update its path based on the current knowledge about the environment. In this video, it can be seen how an AV is exploring the same structure as in the autonomous inspection video earlier. but it's doing so without any prior knowledge about the environment. It uses the boundary or the frontier between what has been explored so far and what is still unknown to find new viewpoints and generate new information that would generate new information about the environment. And while doing this, it's also performing the autonomous relocalization whenever it's needed. And in the video, you can see we use an Octomap. As we don't need too much detail about the environment, this is also plenty enough information to use for planning. The green boxes in this map is what is currently the frontier, so that is where potential new information exists. So the robot will try to find new viewpoints that will have a good information both about the potential new environment as well as keeping old points that it had already seen prior into its frame of view, so that it can also keep a quite high confidence in its localization. For robust and safe autonomous operations, it's necessary to avoid collisions with the environment, which can be achieved by path planning. Likewise, when following a planned path and the map is updated, the path needs to be verified such that it's still valid. If it's not, so that the mapping system has found something in the environment that obstructs the current path, the path which has currently planned needs to be either repaired or it needs to be replanned. One form of repair we can apply is to reduce as much prior information as possible. And we do this by always saving a search tree from previous iterations. And then whenever we have new information about the environment, we prune these search trees so that we at all time keeps a tree that has only valid paths within it. So as soon as we find that our path needs to be repaired or replanned, we can use this prior information and just do a few iterations to solve for a new path instead of replanning from scratch, which will save a lot of time over long term. So where it can be seen is in this video. Here, where it has first planned, kept all of these blue branches in the search tree, and instead of replanning all of these from scratch instead, it only needs to expand on the green ones to find a new valid solution. So, and this planning is taking into, in addition to taking the environmental constraints, it also includes kinematics of the vehicle as well as the sensors and the limitations of the sensors it's equipped with. And by including the kinematic constraints as well as the information about the sensors, we can also include uncertainty during planning. And as seen in the left image, you can see ellipses representing the uncertainty of the robot, which can be propagated along the path to reduce the chances of collision due to the error in post-estimation over time. So a last thing I want to share before I'm finishing is an interesting thing we saw happen at multiple occasions when using autonomous relocalization. In the images to the left, it can be seen the AUV moving around the corner, and while doing so, it lost track of the prior side. And when it came to the other side, it started a new map there, and the autonomous relocalization procedure was started. So it would then keep the new map in memory while autonomously moving back to the prior side. We're able to perform a map merge. And at this point, it now has two connected maps on both sides of the structure and can again safely move around the corner without losing track. And this was a very interesting behavior of the autonomy framework. that we did not necessarily predict. But it shows a great advantage of the autonomy as well. And with that, I'm finished for my part. And if you have any questions, please feel free to ask them. Thank you.
Where you see the applications for this going forward?
Yes, so our next step is to test this in more real scenarios. Right now, we have mainly tested it in our tank with artificial structures, but we're soon going out to test this at wind farms. And in the video playing now, you can see how it is autonomously exploring a wind farm, which we have no information about at all. This is also to be later included to do cooperative inspections, autonomous exploration and inspections of structures where we have multiple vehicles working together, both on the surface and subsurface.
Thank you. That's really useful. So if we pass to our final speaker today, Yaniel.
Good morning, everybody. Thank you very much for being here. So I'm Yaniel Carreno. I'm a PhD student, final year of my PhD at the Edinburgh Centre of Robotics. And I'm also a research assistant in the ORCA Hub project. So today I'm going to talk about our work in AI planning for long-term autonomy. So basically it's like another level up, considering what Tomasz and Jonatan were discussing before, and how we can integrate in some way all their wonderful work in an autonomous framework that is able to deal with a set of conditions of the environments, the uncertainty, and make the system robust enough to deal with all kind of unexpected behaviors and missions that we can have on the water. So long-term autonomy for the underwater domain basically is one of the most important issues that we need to consider when we are implementing a mission in this kind of environment. So real-world applications for these autonomous systems requires the implementation of goals, tasks, and missions in dynamic environments. And basically, because the characteristic of the mission so many times is required to implement coordination and collaboration between multiple robots that present different capabilities. And obviously, because we have a set of robots with all these capabilities, we need to look for a solution that deal with all the properties of the environment and the properties of the robots. So the solution for these problems obviously consider the search for an execution of a sequence of actions that leads the robot from this initial state where they are to a final state where we achieve all the goals in the mission, considering mission constraints and the requirements for the implementation. So basically, task planning, what it's doing is trying to develop a solution for multiple robots or for a single robot to achieve persistence and robustness to individual platform failures and improve mission execution in terms of the timelines and the quality of the intelligence gathered. So obviously, in the context of this project, we have been working with multiple robots with different capabilities. And what the connection is basically task planning out the work that we are doing. We are aiming to allow the system to be embedded in different robots, independently on the characteristics that they have. Obviously considering the sensory system and actuators that they have. So if we talk about, today I'm going to just focus in a single robot. So it's basically the blue Rob 2, and we call it Dora. So basically I'm going to describe now what are the different parts in the framework that we need to consider when we are implementing task planning. So the first one is how we achieve the initial model that describes the characteristic of the environment. And there, obviously, we are considering about the different features that we can have on the water, but obviously all the elements associated with the robot characteristics. The second important element to consider is obviously the specifications of the mission. So there we need to think about what are the goals, but also the constraints. For example, we can have, when I'm talking about constraints and metrics, we're considering what is the kind of time required to implement the mission, and all these elements that allows the system to reason what is the optimal solution to deal with the problem. And these two elements are part of the automated planning system. So are fit in the automated planning system, which actually deals with the temporal requirements, concurrent action execution, incomplete knowledge that we can have in the system, and the coordination and collaboration between robots, if that is the case of the mission. And obviously, there are three elements that we define here in the automated planning system are the main important parts. So the first is actually how we can allocate the tasks in an optimal manner in cases where a single robot is not able to implement the mission. But then obviously how we generate a solution to that mission, and how the knowledge that we have can be, this initial knowledge that we have from the environment and from the robot can be increased in order to obtain a final, better solution. And finally, one of the most important parts in my mind is how we close the loop in some way. And that is related with execution. Obviously, there we are considering how the system deals with replanning during the execution of the mission. But then I'm replanning, I'm saying, when I talk about replanning is what happened when this initial plan, that is that sequence of actions to implement the goals, is not able to be executed completely with a good quality. I am making it necessary to replan this initial mission. But obviously, how this replanning affect and deviate from this original mission solution, and how we can redistribute tasks in cases where some of our robots is not able to finish their initial goals. So, taking into account this information, my talk in terms of the task planning will focus in two main areas. So the first one is think about when we have a fleet of robots and how we optimize this, let's say in a macro way, the final mission that we want to implement. But then what happened when we analyze individually each robot during the execution of the mission? So focusing first on task allocation. So we have been doing some work in the area of task allocation in order to ended up having an approach that allocates mission goals based on the characteristic of the environment and the characteristic of the robot. So we managed to have a solution that deals with the scalability issues that is one of the main elements to consider. But obviously the redundancy in the sensory system, when I'm talking about redundancy, I'm saying, let's say that some of the sensors may fail during the mission. Is that still possible to continue with this action implementation, or is that necessary? Do I need to replan, or do I need to ask for help to other robots in the environment? And finally, how we can, for example, reduce the planning times in our implementation. So in this case, for example, I would like to show you what is one of the applications that we have in this case. For example, we have multiple robots in the environment that they need to implement different tasks associated to turn valves in the structures, but also they need to sample the terrain. Here you can see actually the low-level algorithm doing the mapping. And this kind of distribution of the goals is something that we managed to optimize considering the capabilities of the system. And finally, we have a decentralized strategy. Obviously, that is one of the main elements because we are working in the underwater domain where we have different constraints associated with communication. And we want to, from the beginning of the mission, to obtain a solution that deals with in a better way with the distribution of goals. So now, focusing on what happened when we already have an optimal distribution of goals. Each robot knows what they need to do. What happened during the execution? Well, first, I would like to talk about how we can achieve robustness and adaptability in our system. And one of the first elements is obviously we were focusing on trying to end up having a planner that deals with the information from the environment, the uncertainty from the environment, in order to provide a solution that considers temporal constraints associated with the time to implement the mission, but perhaps we can have a solution where, which is actually the example. In this case, we have surface robots and underwater robots. And during the implementation of the mission, the robot needs to recharge, needs to go to the surface and recharge with this autonomous surface vehicle. So in that cases, there are some particular constraints because the robot, the surface vehicle can be in that position just for single time or particular time slots. So in that case, we need to have a plan that considers this kind of temporal constraints in order to solve the solution. But at the same time, our framework considers the uncertainty in the environment. And this is the second strong element, in my opinion, that we can deal with in our solutions. That, for example, imagine that we need to go to this particular structure and we need to close a valve. But obviously, we don't know what is the state of that valve. It can be open, it can be closed, but we need to close it. So basically, when the robot goes there, it needs to sense and it needs to get information, real information at the execution time in order to deal with that situation. This is something that obviously we can do with a low-level algorithm that is not necessarily just to deal with the task, needs to be evaluated by the task planner. However, we introduced that in our solution at the high level because we need to still keep all this reasoning about the time for the implementation. And then we ended up having like a temporal contingent plan that reasoned about the incomplete knowledge of the environment, at the same time consider temporal and numeric constraints. And that reduces the mission failures because, and reduces as well the replanning, the number of replannings during the mission, because in the kind of environments that we are working, there are a set of problems that can be solved using this temporal planner. And we avoid situations where we need to replan, and because the dynamic of the environment, that replanning will take a particular time, even when it's small, it's not always the best solution. This is the first element that we consider. There are particular type of uncertainty that we can deal with a temporary contingent planner. But obviously, during the implementation of the mission, there are other set of problems that we can face that can affect the solution of the implementation of the plan. And then is when C came, basically the situation, evaluation, and awareness that Jonatan was mentioning initially. And this is basically our framework. And this framework is dealing with another set of unexpected situations that are not considered in the initial plan. So we have an initial plan, which is actually a sequence of actions. And what our system is doing is taking all the information that the plan execution and the sensing information like is, for example, processed by the work that Tomasz was initially describing, in order to provide replanning, provide optimal plans that deal with these particular failures. At the same time, we keep implementing the set of goals that were initially defined, which actually are basically my mission requirements. So in this case, just to put it in the context, I think Jonatan explained very well what are the characteristics of this mission, the mission that we are trying, we accomplish here. But imagine that this is the original plan that we are implementing, and when we were doing this mapping, we realized that we lose track from the features, and then a new plan, a new map is being built. So this is not optimal. In that cases, we will receive this information from the sensing system, which actually will connect with the C, and C will provide intermediate mission requirements and knowledge to the online planner in order to replan for these particular failures, but actually allows the system to move on from this not optimal states, these states that are failure states. And after that implementation, the system reasons about, okay, this is the sequence of actions that will move me from this situation, and then I will keep implementing the mission. Our system is able to maintain the quality of the information that we have gathered, and obviously the mission operation over a long-term period, because we deal with multiple failures that are considered by C, and we have solutions that deal with that particular characteristic of the implementation for that particular failure. So if we put in terms of the context of what we have in the execution of system, basically we start ORCA in some way with this framework. It's a framework that actually we have 4 main elements connected with the world. First, the mission interface, the planning interface, execution interface, and the robot. But then we have been working to build during these years, and I think is wonderful, as first a system that deals with this kind of optimization of the allocation of the missions. At the same time, it takes into account the information that is known at the initial state, a set of information. But we also have C that is connected to the execution in order to deal with the adaptability of that initial plan that will require to move on from these failure situations associated, for example, with the battery level or not optimal mapping of one structure. And finally, we have system connected with the runtime plan verbalizer. So basically, we can have information on how this plan is being implemented, but more importantly, the system is able to take information from C to describe why my initial plan can be deviated. This is the case that, for example, we have a failure, and then the robot needs to replan, and obviously the set of goals that we will have in our recovery plan is completely different to the original. In that kind of cases, the operators can be, obviously because we are talking about an autonomous system, the operator can be a little bit lost of what is happening. And obviously, if we have this plan verbalizer, it is providing, okay, this is the kind of failure, and this is the kind of plan repair that we are, the system is providing in order to deal with this situation. So basically, we ended up having a robust system that at the same time can interact with different other elements in the mission. Like it can be, when I'm saying about the elements, let's say probably different robots, or perhaps an operator if it goes to the surface. I would like to finish talking about this particular kind of solution, because I think in terms of adaptability, we would like to focus on that kind of actions that we can have between multiple robots, and robots working in different domains, surface and underwater. So we have, imagine that we have this kind of plan, which is a sequence of actions that will take a particular time to be implemented. And this particular action here is a coordinated action. So it means that it's both robots needs to be in the same location, executing same action. That happens in situations perhaps that the robot needs to refuel. So basically this, the AUV will go to the surface, and the surface vehicle will support the refueling. This is the original plan. But what happened if during the execution, and now I want you to understand, to think about what we were discussing before, we have a failure in that initial plan. And we say that our system was able to provide a recovery plan that perhaps will have different type of actions to deal with this failure in order to maintain the robot working, but at the same time bearing in mind that it needs to finish the other task. In this kind of situations, what can happen if we don't is like we can end up being in situations where perhaps this action is not happening anymore at this particular time because all these new actions needs to be replanned because there is a failure at this particular time slot. But what our system and what we are working right now is thinking about how we can keep adapting this plan in the at this position, keeping in mind that we need to keep implementing this particular goal at this particular time because there are other robots that needs to go there to execute a coordinated action. And then there we are just like increasing the robustness of the system. We are we know that we have some failures associated with this implementation, obviously, and perhaps what is happening with our system is just like some actions that were previously implemented before this one needs to be moved later. And then this is example for A4 and A3. But at the same time, we maintain we allow the system not to replan for the second robot because it goes there and it realized that the other robot that is required to implement the mission is not there anymore. So we are really thinking about beyond the adaptability of a single robot plan to think about adaptability of the whole system. And this is, I consider that is something quite interesting and quite challenging from our side, but it will provide very good results in the implementation of the final solution. Final takeouts, basically, we are working on shared autonomy for interactive robots, knowledge transfer across autonomous system, Missionsolvability and adaptability, opportunistic task allocation in these cases, and more continuous time, because obviously we are actually interested in maintaining the operation more realistic as possible and maintaining long-term autonomy, definitely. So thank you very much. I'm happy to answer any questions if you have any.
Thank you, Yaniel. That was really, I was going to say it was helpful for me as well. It's great to hear all the progress being made. I should say the ORCA Hub has been running 3 years now, and I can see there's going to be even more work to be done over the next year. So I'm really looking forward to seeing the progress. Just a question from me while I monitor and see if we have any others come in. Are you planning to, have you got any further presentations coming up or conference presentation publications on this work? Just if anybody's interested in finding out more.
Well, we actually, we have at least 3 publications coming up soon associated with this particular work. I think Jonatan actually was putting them as reference. Good Jonatan for doing that. Basically, we have some work in ISHCAI and ICAPS this year describing some technical elements associated with the implementation of these algorithms. How is that being implemented? Obviously, what is the kind of solutions? But I think at the end of this year, we will have at least another 2 publications finished describing this particular final topic that was discussing. And I think, in general, it has been like a quite productive year from our side, basically because right now we are in the position to use the autonomous robots, the real robots, not just in the underwater environment that we have in Heriot-Watt in the lab, but basically doing experiments in real environments. And I consider that in some way ORCA has provided framework, have provided the opportunity to talk with many industrial partners that they are doing wonderful work to support our research and integrating in some way our ideas in real market solutions that at the end is what we are expecting. See our solutions in some real applications.
Yeah, that's great. Thank you, Yaniel. So I don't see any questions come in. We have a very quiet attendee today, but I'm sure that people will follow up with you. We have our website you can go to where we'll have details of upcoming events. And there's also a general contact there. So if you do have questions for any of the speakers and you'd like to follow up afterwards, then please do so. Otherwise, I would just like to thank all of our three speakers today. Some really great talks, and looking forward to hearing further results coming out later in the year. So thank you, everybody.